In this video, we're going to talk about critical points of functions of several variables. So recall the situation if you have a function of one independent variable. A critical point, some books have different terms for this, but a critical point of a function f of x is a point x where either f prime of x is 0 or f prime, and this is in the domain of the function f, where either f prime of x is 0 or f prime of x is undefined. So for instance, if you have something like f of x equals x cubed minus 3x, then f prime of x is 3x squared minus 3. And if you set that equal to 0, you can divide both sides by 3 and you get x squared minus 1 is 0. And then this factors as x plus 1 times x minus 1 equals 0. And so you get x is equal to negative 1 and x is equal to 1. So these are the critical points or critical numbers, depending on the book, of your function. So these are the critical points. There's two critical points. Of the function. And you could have something where the derivative is undefined. So for instance, if you have f of x equals the absolute value of x, then f prime, so what happens is f prime of 0 is undefined, but everywhere else, if x is positive, f prime of x is just the derivative of x, which is 1, and if x is negative, f of x is just negative x, and so f prime of x is negative 1. So what this means, and notice that 0 is in the domain of f, so the only critical point of this function is x equals 0. And the significance of critical points is that this is where the local maxima and minima can occur. So if you have this function x cubed minus 3x, this is going to have, so if you look at the graph of f of x, what's this function going to look like? It's going to have 3 roots like this, and then it's, okay, I don't want to get this wrong, but I think it's going to look something like this. It's going to look something like this. And the point is that the critical points are here and here, and this is where the local maxima and minima can occur. So there's a local minimum here, a local maximum there, and that's why we are looking for the critical points, because they tell you things about the function, like where the local maxima and minima are. And in this case, for the absolute value of x, the graph is going to look like this. And there is a local, actually, this is an absolute minimum. The function has an absolute minimum at x equals 0. Okay, so that's just a review of critical points from calculus. And now we're going to talk about the analog of that when you have functions of more than one variable. Well, in that case, so suppose that you have a function of, say, two variables. Multivariable calculus. Let's say you have f of x. We would say f of xy has a critical point at the point a comma b if, see, instead of just the derivative being 0, now you have two partial derivatives, right? You have the partial derivative with respect to x and the partial derivative with respect to y. And what happens is, it's if both partial f partial x at a comma b is 0 and partial f partial y at a comma b is 0. Alternatively, you could have one of the partial derivatives not existing. Or the partial derivative doesn't exist. Oops. Or the partial derivative with respect to y doesn't exist. But in all the cases, in all the examples that we're going to be working with, the partial derivatives will exist. Yeah, actually in some books, they only define a critical point to be where both partial derivatives are 0. But technically, yeah, you could have a situation where the partial derivative doesn't exist. I think it's just that in all the examples, we will not have to worry about that. Okay. So really, the main thing is that the partial derivatives are both 0. Well, that's when the gradient is the 0 vector, right? So when this happens, i.e. the gradient of f at a of b is the 0 vector, 0, 0. By the way, this is when you have a function of two variables, f of xy, right? If you have f of xyz, it would have a critical point when all three partial derivatives are 0. Okay, let's look at an example to see what that would look like. So for instance, let's say that you have f of xy equals x cubed minus 3xy plus y cubed. Okay. What are the critical points of this function? Well, we need to find the partial derivatives and see when they are 0. So let's find the partial derivative. Partial derivative with respect to x is 3x squared minus 3y, right? And then what's the partial derivative with respect to y? Negative 3x plus 3y squared. So what we need to do is we need to set both of these equal to 0 and solve for x and y. So we have these two equations. So when you have these two equations that you have to work with, they both need to come true, right? You're trying to find x and y such that both equations are satisfied. The trick is that you always want to work with one equation at a time. So let's work with the first equation, 3x squared minus 3y equals 0. What's something we can do to simplify this equation? First of all, we can divide both sides by 3. So if you divide both sides by 3, you get x squared minus y is equal to 0. So what does that tell you? What's the relationship between x and y? Y is equal to x squared, right? Because you can just add y to both sides, you get y is equal to x squared. So what can we do with that? This first equation, right? This first equation is, it just boils down to saying that y is equal to x squared. I mean, this first equation is like a fancy way, it's like a hidden way of saying that y is equal to x squared. So now we need to bring in the second equation, which is we also have that negative 3x plus 3y squared is equal to 0. Now it might be tempting to do algebra, like factor out the 3 and do something with that equation, but what you want to do with this is plug this in there. You have the y equals x squared and you substitute that y in there. So instead of doing, sort of simplifying both equations, I suggest that you work with the first equation, get y equals x squared, right? Simplify that and then plug that directly in. Once you get y in terms of x or x in terms of y, just plug that into the second equation. So when you do that, you're going to get negative 3x plus 3 times x squared equals 0. And then what? What do you get? Negative 3x plus 3 times, what's x squared? X to the 4th power, right? Equals 0. What did we do with the 2 and the 2? We multiplied them. Remember, if you have a to the nth power raised to the nth power, that's a to the mn. That's the fact that we're using to get x to the 4th. Now we need to solve for x. And how do we do that? We can factor out a 3x. So if you factor out the 3x, you get negative 1 plus x cubed equals 0. And now I have a product. I have this thing, 3x times that thing equals 0. And if I wanted to, I could divide both sides by 3 and then get x times negative 1 plus x cubed is equal to 0. I have a product of two things that's equal to 0, so each of these either one of these has to be 0. Actually, let's write the second one as x cubed minus 1, so because it's more standard. Let's write it like that. Well, so the first case is if x equals 0. In the second case, if x cubed is 1, then x cubed minus 1 is 0. That tells me that x cubed is 1, and now what do? I take the cube root of both sides, so I get x is equal to 1. And since I'm taking the cube root, by the way, I don't get negative 1. So I know that x is 0 or x equals 1. And am I done with the problem? What do I do here? Let's think about what we're trying to do, because there was a lot of steps, and think about what we need to do to finish the problem. The question was to find the critical points. And so we found the partial derivatives, we set them equal to 0, and we're solving for x and y. And we know that if x comma y is a critical point, then either x is 0 or x is 1. So what we need to do is we need to find the critical points that correspond to x equals 0 and the critical point that corresponds to x equals 1. So what do we do with the x equals 0? If x is 0, we need to find what y is, right? So what we need to do is we need to substitute. Which equation are we going to, are we going to work with this? No, right? Because we're trying to find the x and y that makes these equations come true. So you substitute into either one and then see what y has to equal. So from the first equation, well actually you could either substitute in either equation, or since we found that y is equal to x squared, that's even easier, right? So if x is 0, then y is equal to 0 squared, which is 0. So you have a critical point of 0, 0. And if x is 1, then y is equal to 1 squared, which is 1. So you have a critical point of 1, 1. So these are the critical points of the function. So let's just review what we did. We found the partial derivatives, we set them equal to 0, and then you get two equations. The key is to work with one of the equations and simplify that. When we did that, we got y equals x squared. Then you substitute that into the second equation, and then when you do that, you're going to only get an equation with one variable. And once you get an equation with only one variable, you can solve for x using algebra. And then once you solve for x, then you solve for y. You can either plug x into either equation and figure out what y is equal to. Or since we found in this case that y is equal to x squared, then that makes it even easier. Now notice that there's actually a subtle thing going on. So we found that when x is 0, then y must be 0, and when x is 1, then y is equal to 1. But what happens if we plugged x equal to 1 in this equation? Right? If you plug x equal to 1 into this equation, what you would get is -3 plus 3y squared is equal to 0. Now you can add both sides. You can add 3 to both sides. 3y squared is equal to 3. Then divide both sides by 3. Y squared is 1. And then you get y is plus or minus 1. So how come that doesn't show that 1 comma negative 1 is a critical point? The issue is that both of these equations have to be satisfied, not just the first equation. So not just the second equation. If you plug in x equal to 1 into this equation, right? If you plug in x equal to 1 here, you're going to get 3 minus 3y is equal to 0, and then when you solve for y, you get y equals 1. So that explains why 1 comma negative 1 is not a critical point. And so you actually, if you're going to use both equations like this, you have to plug x equal to 1 into both equations if you have a scenario where you get more than one value of y. Because both equations need to be satisfied in order to count as a critical point. The point 1 comma negative 1 satisfies the second equation, but not the first equation. Okay, so that's an example of finding critical points. And in the next video, we're going to talk about the analog of the second derivative test. And in Calc 1, the second derivative test can be used to say whether your critical point is a local maximum or local minimum. But when you have a function of several variables, then things are a bit more complicated. Okay, thanks.